I'd now like to introduce our keynote for today, Kate Smith-Miles. Kate Smith-Miles is a Professor of Applied Mathematics at the University of Melbourne and holds a 5-year Laureate Fellowship from the Australian Research Council. She was awarded a PhD in Electrical Engineering in 1996, following a Bachelor of Science with Honours in Mathematics, both from the University of Melbourne, and has held professorships in 3 disciplines, in Mathematics, Engineering and IT, throughout her academic career. Kate has produced over 250 publications on a variety of applied mathematics topics in modelling and optimisation, with applications in fields as diverse as manufacturing design, epidemiology, neural prosthetics, computer vision, finance, and stem cell modelling. She was awarded the Australian Mathematical Society Medal in 2010 and the E.O. Tuck Medal in 2017. In 2017, she also became the first woman and the first Australian to give the annual Alan Taylor Applied Mathematics Lecture in its 31-year history at the University of Oxford. She has previously served as President of the Australian Mathematical Society from 2016 to 2018, the head of the School of Mathematical Sciences at Monash University from 2009 to 2014, the head of School of Engineering and Information Technology at Deakin University from 2006 to 2009, and is currently finishing a 3-year term on the Australian Research Council's College of Experts. She is chair of the advisory board for the Australian Mathematical Science Institute's Choose Maths program, aiming to increase female participation in mathematics, and has created a YouTube video on Mythbusting Mathematics, along with public lectures to encourage all students, especially girls, to see how mathematics can shape and influence the world. Please welcome Kate.
Thanks very much. I certainly will be talking to you about Mythbusting Mathematics, but the title of my talk is perhaps a bit broader than that in reality, because how often do I have a chance to speak to so many maths teachers in one room at the one time? So I'm taking full advantage of the opportunity. There's quite a few things I want to discuss with you today. So it's not just about Mythbusting Mathematics, how we can challenge student perceptions. I know you've all heard students complain that maths is irrelevant or boring or too hard. We're going to talk about that for sure. But there's a bunch of other things I want to talk to you about. So 3 parts to this talk, and I'm keeping an eye on the time. So part 1, yes, we'll talk about Mythbusting Mathematics. We're going to look at those myths, why they exist and what you can do to try to debunk them. Part 2, I'd like to give you some ideas for what you can do in the classroom to inspire curiosity, because that's what mathematicians are. We are curious about the world and we develop new mathematics all the time. I think a lot of students think that mathematics is some dusty old subject that's all in the textbooks and they've just got to memorise everything. Maths is evolving all the time, and I want to give you some ideas of how you can show your students that, what mathematics is left to invent. And I want to share with you the tale of a really remarkable female mathematician. It's not me, it's somebody I find really inspiring, and she should be a household name, and I want to share that with you. And then finally, part 3, hopefully I get time for this, to reflect on my personal journey. I want to share with you what I was like when I was 17 in your classroom, and what my maths teachers should have told me, and one inspiring teacher who really is the reason that I'm standing here today. Okay, so let's get cracking because I've got a lot to cover. So part 1, let's bust some myths. So I'm sure you've all heard some of the following myths. Nod in appreciation, recognition if you hear these in your classroom all the time. I can't be a mathematician because I'm not a genius. Like, people believe you have to be a genius to choose to become a mathematician. Girls aren't as good at maths as boys are. Maths is really just about adding up numbers. It's so boring. Why do we need it? We have calculators. Maths isn't relevant to the world or my future. And there's no new maths left to invent. Like, why would you do research in maths? What's that about? Okay, so those are some popular myths that I hear a lot when I tell people that I'm a mathematician. Their reaction is usually one of those. I hated maths at school, or maths is too hard. So I have a video on YouTube. I'm not going to stand here and regurgitate that. You can watch that. I really encourage you to share the video with your students. It goes for about, 15 minutes or something. And we discuss all of these in the video. But I'm going to give you the sort of quick recap of that. So you can just search on YouTube for Mythbusting Maths, or search for my name and you'll find it fairly quickly. Okay, what I want to talk though, so we'll discuss those, but what I really want to talk about is where those myths come from. Why do these myths exist in our society? So I know you all know that student attitudes towards mathematics are formed very early, and it's very hard sometimes to undo the perceptions that they have. They're deeply ingrained beliefs that maths is too hard for some of them, or it's boring, or it's irrelevant. And once they think that, it's very hard to shift that thinking. And it often reflects the attitudes that they're growing up with in their family. The number of times you have parents who will say, "Oh, I always hated maths at school," and children grow up hearing that. So maths is kind of like this hard thing. Or their parents will say things like, "Well, I hated maths at school, I failed maths, I didn't continue with my maths, and I'm just fine. Like, everything worked out just fine for me, I didn't need maths. All that maths that they taught me at school, never used any of it." Right? So students grow up hearing these kinds of things, and as teachers you have to kind of fight against that somehow. But we have to challenge these perceptions because unfortunately some of their parents don't seem to realise that if they cut themselves out of considering mathematics in the future for them, studying advanced mathematics in high school, going on to study further mathematics or quantitative subjects at university, they really are cutting themselves out of a future workforce. And I don't know that their parents in previous generations have fully appreciated what the future workforce is going to look like and the importance of all students keeping their options open. So we do have to challenge it. Every student deserves an equal opportunity to have a strong future in that workforce, where these high-level numerical skills and analytical thinking are going to be essential. They can't drop out too early. So, why do we have these myths? I think there's many reasons, but I think there are sort of two primary things that I'd like to discuss with you today. First of all, I think there's a real lack of understanding in society of what maths actually is. People think that they know what maths is, but I challenge that view. I think we don't communicate enough about what mathematics is to someone like me. And so because they don't really understand what maths is, they're getting maybe a biased perspective of it from the school curriculum. They don't really see what it's good for and why they should study it. And the second major contributing factor, I think, is this prevailing belief that you either have a maths brain or you don't, right? Which is absolute rubbish, but we'll talk about that. Okay, so what is mathematics to most people? If you grab a random person on the street and you ask them, have you studied mathematics? They'll say, yes, I studied a lot of mathematics. Most people think they know what it is because they've been studying maths since they learnt to count, right? As they're walking up the steps to kindergarten and people are saying 1, 2, 3, that's the beginning of their mathematics journey. And even if you think about it, I don't know, 13 years of school, an hour a day of maths, let's say, how many hours does that add up to? By the time they finish school, I think we're talking about 2,500 hours of mathematics study, not even close to the 10,000 hour rule. You all know about the 10,000 hour rule to become highly proficient at something, to have mastered something like being able to play the violin or something. 10,000 hours, or athletes in the Olympic teams, 10,000 hours to master something. They don't even come close to that in their mathematics journey, right? So they're not entitled to think they've mastered mathematics at the end of school. But after studying mathematics for more than a decade, you think you'd have a bit of a clue about what it's really about, right? So they're perfectly entitled to believe that mathematics is arithmetic, a bit of geometry, all these kinds of things that they cover in school. But it's just a tiny part of it, right? They haven't really been exposed to what mathematics is really about. And so the mathematics that they have to study at school leads to these common beliefs that it's kind of dry and boring, and it's just quite procedural. And I have, personal reflections on this as well. I remember being in grade 3 and being away from school one day where they learnt long division. And I came back the next day and everyone was doing long division and I didn't know how to do it. And for a moment there I felt like, oh, I'm not good at maths because I don't know how to do this thing that everyone else can do. The procedural thing, it's not about how you think mathematically, it's about whether you can follow the steps of a procedure. And a lot of students think that mathematics is completely just procedural and you're good if you know the procedure and you're not good if you can't do the procedure. But that's not what maths really is. It's not about procedures that have to be drilled. Another belief that students infer from what they study at school is that maths is useful for everyday things. Right? We work really hard to show the relevance. Everyday, fairly trivial things like how to make pancakes following ratios. If you want twice as many pancakes, what do you do to the ratios? Laying brick patterns using geometry, or figuring out, how to place a ladder on a wall and what angle it should be and what length it should be. These kinds of applications, they're real world-ish, but not inspiring, and a lot of students finish their mathematics studies at school and believe that that's what maths is good for. Well, I can make pancakes without following ratio recipes, and I can place a ladder on a wall without getting a protractor out and measuring an angle. No worries. And of course, then they have their parents with this kind of counter argument that actually I don't even need maths for these everyday applications, right? I survived just fine when I dropped out of maths and I've never needed it. So yeah, these are the perceptions. And the idea that maths is just completely irrelevant to the future. They can't see it. If they're thinking about when I grow up I want to be a doctor or a lawyer, don't need maths. Right? They're not seeing the many, many career paths where maths is highly relevant. So what we need to try to impress upon our students is that mathematics is a foundation for some very powerful things in society and a whole lot of beauty as well. And we can't forget to emphasise that, because some of your students will get that. They'll love that. I like to think of it like this: the difference between the maths they learn at school and what maths is to someone like me. There's an analogy with music, right? So students who are learning a musical instrument have to put in the hard work and do the scales and the technical exercises. They just have to, or they can't express what real music needs to express. They can't play the real pieces until they've done that foundational work, right? Same with English. They have to learn to spell words, they have to learn grammar and syntax before they can write masterpieces. It's just, we understand that in certain disciplines, that there's a foundational work that has to be done before you get to see the real beauty and power of a discipline. And so the kind of maths that they're learning at school is foundational, and it's preparation for something much more powerful that unfortunately most of them don't get to see because they haven't done the 10,000 hours. So the challenge is, how do we expose students to that real power and beauty of the more significant maths, like the real maths that I'm talking about, not arithmetic and some trigonometry? How do we expose them to the potential of mathematics and inspire them to want to learn more beyond these foundations that they have to learn at school? So the foundations that they're learning at school are foundations to have profound impact in the world, and I'll share with you soon some of the many ways that mathematics can do that. But it's also foundations for their future, the jobs that they will have, the future well-paid jobs of our current generation of students in the future, where they have to have that analytical and logical thinking that is only taught by studying higher level mathematics. Yes, you develop a little bit of logical thinking and analytical thinking by learning procedures like long division, but it's not really the development of the analytical mind that higher level mathematics gets them. The ideas of proof and things like that are really important. So there's a depth and breadth in mathematics that the school curriculum simply can't explore. You just don't have time. And yet we have to give them a heads up about what's coming if they keep going. So we need students to realise that more advanced mathematics is really important for tackling some really important problems, and just like mathematics has done for many, many centuries, it's a dynamic, adapting field that responds to societal need. Right? When society has a problem and existing mathematics can't tackle it, mathematicians, rally around and try to develop new mathematics that can solve that problem. And I think we need to share with our students perhaps a little bit more of the history of mathematics, why we have the mathematics we have, why it was developed, what it was in response to, what powerful things it enabled to happen in the 18th century or whatever when it was developed, and keep going in the future, understanding the future challenges and the maths that will have to be developed. So it's a challenge for curriculum and pedagogy in how to get the balance right between making sure that all students have the foundations, the everyday numeracy skills that will be important if they just need to be functioning in our future world, not as mathematicians, but just as quantitatively minded people, but also to try to motivate a larger number of students, larger than we're currently motivating, a larger number of students to try to explore really advanced mathematics and creative mathematics, the kind of mathematics that will be needed for problem solving for the future. We have to motivate a higher number of students. We have to help them believe that they're capable of being part of the mathematical solutions of the future. So how do we ensure that students can see the basic concepts that they're getting in the school curriculum and can see, even if you don't have time to go there, but can see and understand how that could lead to more significant real-world problem solving in the future? And I'm sure many of you have seen this movie, Hidden Figures. If you haven't, I highly recommend you watch it, not just for the gender issue, but just for the notion that mathematics can be really a powerful tool and can tackle some really important problems. There's a scene in there where there's one of these women on the blackboard, and there's something to do with parabolas there and how we're going to get this astronaut back to Earth safely. And you don't have to go through the mathematics in your classroom, but when you're teaching parabolas and ellipsoids and things like this, just reference to this kind of stuff, that it's this kind of mathematics or advanced extensions of that kind of mathematics that solves some really important problems for NASA and things like that. It's an opportunity to connect and help them see how some of the fundamental ideas that they're learning have more advanced extensions that have really important applications. And there's various websites you can go to and get inspiration for how the foundational concepts generalize and extend to tackle more significant applications. So I'm sure you hear frequently, why do I need to know this? So here's my simple answer. You need to know this foundational mathematics because mathematics is a language that we use to describe our world. With that language, we can prove facts. Right? We live in a world where people believe things without evidence. Right? Mathematics is the truth. Mathematics is about proof and logic and being able to put arguments together that where one argument follows from the next to the next to the next, and you draw a conclusion that's valid. Mathematics gives us the language to prove things and to also estimate uncertainties. There's so much uncertainty, and we need to have the quantitative rigor in how we can estimate the probability of something happening. To guide our decision making and our debates that we have as a society. With mathematics, we can model what we see. Right? Traffic flow, traffic congestion. It was awful getting here this morning because of traffic mess. We can model what we see with mathematics. We can predict what would happen if we made some changes. What if we, made that green light stay green just 5 seconds longer? What's going to happen to the traffic flow? And with that prediction, we can then try to make the right decisions. Maybe it's not 5 seconds, maybe it's 7 seconds. What does it do to the system? With mathematics, we can model our world, we can predict responses, and we can improve our world. Right? So for people like me that like to use mathematics to have a positive impact in society, this is beautiful. This is a language that I can use to feel like I'm making a difference to the world. We need to impress upon our students who want to change the world that you don't have to do law or medicine to change the world. If you love mathematics, you can learn this language and you can have an impact in the world through this language. Right? So those systems could be traffic networks, it could be the human brain, stem cells, stock markets. There's so many examples of where mathematics is this generic thing that models what we see and can improve what we see. So the opportunities for having a positive impact are endless for those who have learnt to speak this powerful language, and I think that's a really important message to share with our students. And it's not just about having an impact in the corporate world. Yes, they can get high-paying jobs in industry, helping companies make more money. A lot of them are not going to be motivated by that. A lot of them want to change the world for social good as well, and there's plenty of ways that mathematics is being used to help, even climate change and environmental thing. So you work for a company who's trying to maximise their profit, but at the same time they have to reduce their carbon emissions. How are they going to do that? Right? So I'm currently partnering with lots of industry partners. I just signed something yesterday to work with 11 industry partners who are all trying to make optimal decisions that have conflicting objectives, and many of those objectives are about social good and climate and energy minimisation as well as profiteering. So everybody needs to learn to speak this powerful language fluently. Just like we make them learn to speak English fluently, they should speak mathematics as well. So I just want to share with you some ideas of how mathematics, mathematicians, a little bit of unsung hero as we see in this Hidden Figures movie, the hidden work of mathematicians, things your students may not have thought about. Who works out the traffic light sequences when they're sitting there? They should be thinking, as they're moving around our world, they should be thinking about all the places where mathematics is hidden. Get them to write an essay about it. On your journey to school today, how many things did you see where mathematics is actually driving it? Who works out which trains we need on which lines at which times? Who works out when the aeroplane should take off and land, when it's safe enough that the turbulence in the air from the last plane that landed has settled down and it's safe for them to go? Who works out what the weather forecast will be? Every morning when they check the weather forecast to see if they need their jumper today, think about the mathematicians that presented that forecast. Who works out which stock investments funds should buy so that their parents' superannuation keeps growing? Best premium to charge insurance customers that balances risk versus retaining customers. How much radiation cancer patients need in various parts of a tumour. We want to choose the radiation and the direction and target it so that it zaps the tumour but doesn't kill all the surrounding healthy cells. Mathematicians work on these problems. Who works out if a credit card application is fraudulent? Or when you're trying to make a mobile phone call, which frequency you should be assigned in a very limited bandwidth so that you have a good quality of call that doesn't interfere with anybody else near you that's also making a phone call. People don't think about all the mathematics involved in everyday things. Now, so who works out all this? Of course, mathematicians do, but I've worked on every single one of those problems in my career. Every one of those I have worked on, right? It's a rich and diverse and fascinating collection of real-world problems where mathematics has the answers. It's not just those problems that I've worked on in the past. Mathematics is so critical for the problems that we will face in the future. So climate modelling, stem cell modelling, therapeutic medicine, outbreak detection, trying to work out whether we should shut down schools or what intervention strategies we should implement when we start to get the earliest possible indicator that there might be a problem in our society, like an epidemic of a disease. Biosecurity, protecting our food supply, being able to recognise when there's threats there and what actions we should take. Traffic modelling, of course, sourcing new renewable energies. All of these problems need mathematicians to think and come up with solutions. So I hope we can inspire the next generation that they really need to speak this language to be able to be part of the workforce that will be tackling these problems. Other things you can say to your students if they don't know what it means to become a mathematician. Every year there is a survey of the top jobs in the world. They survey about 200 jobs and they look at criteria including the work environment, the income, employment outlook, physical demands and stress. So guess what the top job in the world is? Mathematician. Top 5 jobs: mathematician, actuary, statistician, same thing, and some other stuff. But if you share this with your students, you will inspire them to have the top job in the world. Actuary is just really a mathematician that's concerned with predicting when you're going to die, and statistician is just a mathematician that looks at data. And
software engineer has a partial mathematics aspect to it.
It's true, and a lot of biologists, increasingly biologists, need to be mathematically, quantitatively trained as well. Look, from year to year, the order might change around a bit, and sometimes like operations researcher is up there, which is my style of mathematics, but it's always something mathematical that's in the top jobs. And you can share with them, who remembers what Homer does for a living? Is he a mathematician? What does he do? Nuclear power plant operator. Really wishes he did a mathematics degree. Okay, so please share with your students the fact that being a mathematician is widely recognised consistently year after year as the top job in the world. Okay, so you might be able to convince your students that maths is really important and that someone in the world should become a mathematician. Maybe one of their friends can become a mathematician, but they don't feel that they should because they don't have a maths brain, they think. Okay, so you've managed to convince them that maths is important, but not for them. What can you say? So, of course, early negative experiences are really harmful to students' perception of their own ability. As I said to you myself, away from school when we learnt long division, came back to school the next day, oh, I'm not good at maths anymore. I was good yesterday, I'm not good today. Right? So we have to watch out for these experiences and the impact that they have on confidence. Confidence is really key with mathematics. Are there gender differences? There's evidence that girls disengage in maths earlier and in greater numbers than boys, that girls can be very affected by confidence issues, but there is no evidence that girls perform worse than boys. In fact, there was an email I got 2 days ago about a new study that's come out from some researchers at Melbourne University who have done sort of scans of brains of girls and boys doing mathematical stuff. There's no difference in brain behaviour when male and female students are doing mathematics, and there's no evidence that girls perform worse. There is plenty of evidence that girls are less confident, and that's something that we need to address. So the AMSI Choose Maths program that I chair the advisory board for has shown confidence for all. That's my little mathematical notation. It's the only maths I've got in this slide, in this whole presentation. But confidence for all can be changed with simple intervention exercises. I don't know if anyone from AMSI is here today, but please grab them and ask them about what they've been doing in their outreach activities, working with school students and teachers on the power of yet. Okay? There's a difference between saying I can't do it or I can't do it yet. Right? It's how you think about it. You know, it's a little psychological thing, but we have to really focus on raising student confidence, and if they can't do something, they can't do it yet, right? But they work at it, they will. And we have to think about maths anxiety, this nasty concept of maths anxiety, and how we can use this sort of mind shift thinking to increase confidence and the strategies we employ around teacher training, but also influencing parents and the messages that are being reinforced at home. A lot of maths anxiety is a inherited condition from parents saying, oh, I was so hopeless at maths at school. Yeah? So immediately there's a little anxiety around maths being a bit too hard, or I can't do it because my mum couldn't do it, or whatever. Okay? Okay, so you might be able to convince them that they can do maths. Can't do something yet, but they can do it. I can do maths, but I'm not a genius, right? So I shouldn't do advanced maths. My message here is all students can be taught to think mathematically and solve problems, just like all students can be taught to read great works of literature and decipher the messages that are in there and understand deeply what a book is really trying to say. All students can be taught to think mathematically and analyse problems. You don't have to be a genius to become a mathematician. Of course, mathematical geniuses should become mathematicians, and there's a path for them, right? They go in the international competitions, they win Fields medals, they're brilliant. Let them be brilliant. There's room for many other people to be mathematicians as well that do different kinds of mathematics, that work collaboratively and solve problems and help improve traffic flow and help hospitals sort out their queuing systems and reduce waiting times. There's many ways to be a good mathematician. We urgently need to communicate to change student perceptions and attitudes. We need to communicate what mathematics really is, its significance, and we need to showcase role models who are relatable, because the problem is when most students think about mathematician, they're getting a whole lot of Hollywood stereotypes that are not relatable to them. It's not something that they aspire to be. So back to myth busting then. All of this is discussed in more detail in my video, but let's just quickly whip through what I show in that video. So here's the Hollywood stereotype. Mathematician, who wants to be like this? I mean, they're brilliant people, but they're mostly portrayed as eccentric, male, mentally ill, loner types who sit in a room by themselves trying to solve some impossibly hard maths problem that no one cares about for about a decade until they slowly go crazy. Right? Who wants to grow up to be like that, right? So, you know, if that's the perception of what a mathematician is, we've got a battle to fight against it, to show examples of other mathematicians that are not doing that. So we can bust that myth by finding relatable role models to come and visit your school. Go to your local maths department and ask for your most relatable young mathematicians to come and visit your school and share with the students what they do as mathematicians and try to counteract some of this Hollywood stereotype. Most university maths departments have an outreach officer of people who are very good at understanding what students need to hear and finding some of our, master's or PhD students who would be happy to come and talk to students in your school about why they love maths and what they're trying to do with their mathematics. Try to find mathematically trained parents. Over the years, I've done a lot of stuff with my kids' schools, just coming in and working with the grade 5, 6 kids or running enrichment activities. Probably in your school you do have mathematically trained parents who would be willing to come and share what they do in their job that's relevant to mathematics, and try to find some of your alumni who have gone on to study mathematics to come back and share what they do now. Myth about girls can't do maths. Well, you can present evidence to counter that myth. So of all the evidence out there, this is my favourite one, well, until the one I saw last week. This was a meta-analysis of 242 studies that have been conducted over many decades of about 1.2 million people. In this study, they basically said that there is no evidence, there's no difference in performance in mathematics based on gender. Okay, so we can bust that myth. What can you do? You can share that study, you can tell your students about it. You could have a look at what AMSI is doing through the Choose Maths program to support girls and mentor girls, and this whole idea of positive growth mindset, the idea of YET. The perception that maths is just about adding up numbers really, really quickly, because, I can understand why students think that, because we pressure them in primary school to know their times tables super fast, right? It's like a competitive thing. I've seen my son and his friends in primary school, especially boys, super competitive about who can answer the questions fastest. Maths isn't about, it's not a competitive sport. It doesn't have to be, but sometimes the way we approach it makes the kids believe that that's what it's really about. It's not about how quickly, Rain Man can multiply, 7-digit numbers together in his head. That's not what maths is. I can't do that kind of stuff. And I'm a professional mathematician. My mental arithmetic is not great. And it's just because it's a party trick. I don't use it, don't need it. So what can you do? You could reinforce that message I said earlier about the stuff you're learning is foundational, but why the foundational is so important, like scales are to musical pieces or grammar is to literature. What you're learning is foundational. It's not necessarily exciting, but you've got to put in the work, but then try and show them some of the exciting extensions of it. Focus on problem solving rather than the procedural drilling, and try to find ways of helping them see the creativity of mathematics and the elegance and the beauty of it, and there's more of that in my YouTube video. The idea that maths is not relevant to anything, there's so many applications you can talk about of where mathematics is critical for studying climate, modelling disease, therapeutic medicine, improving our world, lots of things you can share with them there. And the idea that all maths has already been invented, it's this dusty old subject that you've just got to kind of work your way through and there's nothing new to do. Well, what can you say about that? I'm going to share with you now some stuff that will help you bust that myth, because it's really about showing them that maths is always responding and dynamic, and new maths comes from societal questions, and we are not a static society. We are evolving rapidly, the kinds of challenges that we face, and maths responds accordingly. So new maths is created in response to society's challenges, and as an example, you could share with them, if you like this idea of, and I know a lot of schools do like this idea of an integrated curriculum, if you like the idea of bringing history, for instance, into your mathematics classroom, and they're learning about, World War I or II or something like that, they could be thinking about what mathematicians were doing during those wars. There's already some great movies like Enigma and stuff like that, and Alan Turing, but there's plenty of times throughout history where something interesting is happening historically, and mathematics has been there in the background, hidden heroes, developing new mathematics to be able to help. So think about World War I. So here we have Edward Busk, who was a pilot, but also a mathematician. So as mathematicians, we can't help it. We are so curious about our world, and because we have the language to model what we see, when we see something, we want to think mathematically about what we're seeing, and we want to think about how we can improve it. So Edward was a mathematician flying planes in World War I and got fascinated by studying airplane stability, and so developed some new mathematics needed to be able to do that, which led in 1913 to the first stable aircraft being used in World War I. Prior to World War I, yes. So, yeah, you're right. But it was because of the mathematicians that during World War I they were able to advance technology. And Geoffrey Taylor, also a pilot and mathematician, got fascinated by parachute dynamics, and so developed some new mathematical ideas to help safely enable troops to land at targets. Of course, they were not the first. Galileo, Newton, in their times, 17th, 18th century questions around military efforts. So ballistics, where are those cannonballs going to land? That's the old parabola there. So, there's a lot of fundamental mathematical ideas that came from mathematicians looking at the challenges of the time and responding. World War I and sound ranging, this question of where are the guns hiding, and this idea that if you hear in 3 different places, you can triangulate and you can estimate where the guns might be hiding. Right? So there's lots of interesting questions that have come from a war context. Now that may not fascinate your students apart from connecting it to history, but think in a modern context. Think about modern versions of the same problem. Right? So as mathematicians, we can take the fundamental idea and generalize to many different problems. Mathematics underpins lots of things in a common way. So a similar problem in a non-war context would be something like this. So in Queensland in particular, they have a big problem with these red fire ants, poisonous. And if you see ants at certain locations, if people report, I saw some ants here, I saw some ants here, I saw some ants here, where are the nests? Can we figure out where the nests might be so that we can eradicate the fire ants? Right? So that's an inverse problem, much like where are the guns hiding? Yeah? So trying to get students to see that mathematically the questions are actually the same. Right? The context is different, but some of the mathematics that's developed, we develop it because it's reusable over and over again to ask different questions in different contexts as society demands different answers. So I want to share with you quickly the kind of mathematics that I do a lot of, which is optimization. So this was a field of mathematics that didn't appear until World War II. So some of the powerful techniques that we now have that are used in everyday applications like Google Maps, for instance, came from the study of World War II needs. So a whole field of mathematics emerged from the decision-making that happened in World War II. Which troops should be sent to which battles? Which weapons should be allocated? When should you do maintenance on planes and ships? Because the military was asking these questions, they asked the mathematicians for their war effort. We're not going to send you off to fight, we're going to get you to think. Think about how to solve these problems for us. And they developed a whole new kind of mathematics to answer questions like this, decision-making questions. Okay, but you can imagine these kinds of questions are also asked by companies that run manufacturing problems, or they have to distribute logistics and transportation problems. Right? So the mathematics is reusable. So all of these questions involve making decisions that maximize or minimize something. Right? Minimize costs, minimize damage, maximize opportunity, while satisfying some constraints on permitted values. So this is optimization or operations research, and some of you will have studied some of that at university. And it's a little bit in the maths curriculum. I think, in further maths, there's a little bit of sort of linear programming, simplex method kind of stuff. My biggest regret about the curriculum is that the serious maths students don't actually get to see that. The serious maths students get to university and they haven't studied some fundamental ideas like graph theory and some basic optimization ideas that are in the further maths curriculum. And I teach them sometimes at third year and they've never seen these ideas, and yet these ideas are so critical for being a really useful applied mathematician in the world. I don't know if we can do something about that, but those ideas should actually be in the advanced maths as well. So, interesting question. So you learn the the simplex method, for instance, and you know how to maximize or minimize something subject to some constraints where the decision might be something like 2.7. What if your problem needed those decisions to be whole numbers, integers? So here we have the famous branch and bound algorithm, which I don't know how many of you know was pioneered by a Melbourne woman called Alison Harcourt in 1960. So the branch and bound algorithm is like linear programming, but it's integer linear programming. And it gives you a solution of whole numbers, which of course we need for so many practical applications. Because don't think you can just take the fractional solution and round to the nearest integer and it's going to be optimal. Right? Rounding to the nearest whole number doesn't necessarily make the solution optimal. She proved mathematically how you can do it to get the optimal integer solution. So here she is around that time. She did a master's degree at Melbourne University on linear programming. And then she went over to the UK, as people did at that time, to get some broader experience. And she ended up working in London as a research assistant and answering this question about, well, how do we adapt the linear programming idea when the solution has to be whole numbers? And she ended up developing what became known as the branch and bound algorithm in a famous paper in 1960. She came back to Australia as a senior lecturer in statistics at University of Melbourne. She completely changed field. At the time in Melbourne, there were no people working in operations research, and she didn't continue with that direction. She worked as a senior lecturer in statistics, where she stayed to the end of her career. In fact, she's still there. She's 90 years old. She's an amazing woman. There was a story on ABC 7:30 report about her. I nominated her for an honorary doctorate and for Victorian Senior Australian of the Year, which she was awarded. Finally, last year, she got an honorary doctorate because she never got a PhD. And yet her work is so fundamental to the whole field that I work in optimization, so fundamental to decision-making out in the world, that it was long overdue, and it was great to get her that recognition. So she should be a household name. Your students should know about her. They can watch the 7:30 report story and some of the media that happened last year and this year. And so, of course, that same mathematics is involved in everyday non-war applications, such as how I got here today. This is not the truth. I did not come from Melbourne Uni. I actually came from the airport because I was in Adelaide yesterday, but I thought when I prepared the slides I was coming. So Google Maps, how to get from A to B, minimising toll roads, turn that option off, minimising congestion, get here in the shortest possible time, that's optimisation. Your students can think about that. They can think about other problems. You can set them tasks where they can just do it in Excel. They can solve optimization problems in an Excel spreadsheet. They don't need to be great computer programmers, although I think most of them are these days. But here's an example, the McDonald's diet problem, right? Suppose you decided to camp out at McDonald's for the day and eat all of your meals at McDonald's, and you want to minimize your costs, but your parents say to you, but I need you to get your nutrients, all right? So I need you to get at least 55 grams of protein. I need you to get your recommended dose of vitamin C and calcium, and they want to spend as little money as possible. This is an optimization problem. How do they look at all the things they could buy, and for each item there's the price and the calories and the fat and the vitamin C and calcium, and they have to figure out how many hamburgers, how many Big Macs, how many chicken nuggets, etc. Oh, there's some salad there as well. How much salad should I buy that minimizes my costs and makes my parents happy that I've had my nutritional balance? That's an optimization problem. They can solve it very easily. In the process, they would learn some very nice mathematics. You can add extra constraints in there if you're also concerned about sodium or fat or iron. The more constraints you add, the harder the problem becomes, and it may become an infeasible solution. The answer may be, sorry, I couldn't actually eat the whole day at McDonald's. Yeah, that's right. Well, that's a nice example of how adding constraints restricts the search space, and sometimes you get an infeasible problem. Okay, excellent. My timing is good, and I have time to share with you now my personal journey. So I hope I've given you some ideas of what you can do in the classroom to inspire your students and debunk some of those myths. And now I'd like to reflect on the inspiring influence of a maths teacher that I had. So this was me when I was 17. The school captain asked us for the yearbook to describe our likes, dislikes, and ambitions. Don't worry about some of these cryptic comments. we don't have time to go there. But I want to focus your attention on what I wanted to be when I was 17. I wanted to get 369 in the exams. So it's not an ATAR thing, it was an Anderson score back then, which I did. And I wanted to work out Kate's theorem and for someone else to use it. Kate's theorem. Why does a 17-year-old want her own theorem? What's with that? So I think I was rather inspired by old Pythagoras. I thought that would be pretty cool to have a theorem named after you. So that's what I wanted. I wanted my own theorem. And I didn't just want a theorem that no one was going to ever use. I wanted to be famous with this theorem. Right? I wanted people to use it. I wanted it to have such impact that it was not a dusty old theorem that no one ever looked at. So, why did I, as a 17-year-old, want my theorem? I actually was training to be a ballet dancer. And I went into year 12 having dismissed that idea. At the start of year 12, ballet was over for me. I was getting too tall and realised it was probably not a sustainable career anyway. And had convinced myself that I should be a journalist because I love writing. I love the power of words, and at that time I hadn't actually considered that mathematics was a language and that you can do powerful things with those words as well. So I was going to be a journalist at the start of year 12. And something happened to me in year 12 that made me change my mind. And that's what I want to share with you because it was the influence of a maths teacher. So prior to year 12, I hadn't thought about doing mathematics. I was good at it, but I didn't consider myself to be a genius. I still don't. Did I enjoy mathematics? Yes, I did. I liked getting the right answer. On that likes, dislikes, and ambitions, you may have noticed I liked pink pencils. What was that about? I had this special pink pencil. It was kind of neat. If it got a little bit wet, it turned into a texter, but otherwise it was a pencil. I thought it was great. But I used to like, when I solved a maths problem, boxing in the answer with my pink pencil so that the markers could see it. There's my answer, don't miss it. I loved my pink pencil because when I got to use my pink pencil, I got to the bottom and I had something to box. I liked that feeling of seeing the answer and knowing that it was right and knowing that if I got it right, I got it right. I got the marks, as opposed to English, where it could be somewhat subjective whether you got full marks for an essay. So I liked that, but I wasn't really passionate about mathematics at that point. There were some confidence issues, still can't really do long division fantastically well. The procedural stuff, I couldn't really see the relevance of mathematics at the start of year 12. But I had this year 12 maths teacher, and she really changed my view. She made me see that maths was more creative than I'd thought, that there were many ways of reaching an answer. And I also saw with her that maths can be quite elegant and that there are some fantastic things you can do. And I talk more about this in my YouTube video. I give some simple examples that high school students will understand of how sometimes there's a problem and you don't know how to start. You just don't know what to do. But then you think of one thing you can do. And, I use a simple example in the YouTube video. But the real example that I'm thinking of here was in year 12, like a U substitute. You're trying to integrate something and you can't think how to integrate it. But then you say, well, let U equal this. And now I rewrite in terms of U, and now I know how to do it. So I solve in terms of U, and then I can substitute back in, and I solve my original problem. Thinking creatively and how to take a problem that initially wasn't solvable, but you do something creative, and now it's solvable, and the elegance of that, I loved that. And so my curiosity was really sparked during year 12. And I got to the end of year 12 and felt like that can't be it. I just want to keep learning more about mathematics. So I decided I wanted to go to university to study more mathematics. She actually tried to talk me out of it. She thought I should do law or medicine. And when I said I don't want to be a doctor or a lawyer, she said, okay, well, what about architecture? She was trying to think of these noble professions because in her mind, mathematics was what she did. And she was a maths teacher and she wanted more for me than that. She didn't want me to just grow up to be like her. She thought that I could do better than her. And I found that really fascinating because she was my role model and I thought how great it would be to grow up to be like her. I thought what a noble profession it is to be a maths teacher. You know, good on all of you. That's what I thought that would be fantastic to be a maths teacher, but she was trying to talk me out of it. She thought that I could aim higher. But anyway, I'd already made up my mind that I wanted to keep learning maths, and so that's what I did. So just very quickly, because I've started telling you about my journey, I should probably not skip any big bits. So I went to university at Melbourne, and I had to enrol in a Bachelor of Arts to do mathematics because I didn't do physics or chemistry, because one of my prevailing thoughts as a 17-year-old, and it's still my same thought, is that I should always just follow my passion. And in school, I was not passionate about chemistry or physics. I was passionate about maths. I did the double maths, but I loved music history and English literature and other things. So I just did what I wanted to do. And the consequence of that was I couldn't get into a science degree because I didn't have chemistry or physics. That's fine. I did a Bachelor of Arts, I did lots of maths, I did music history and psychology, and then I transferred into science in second year because my maths results were good and they let me into a science degree. So that was fine. But I decided on day one of my very first lecture, Monday 9 a.m, that I was going to be a maths lecturer. And that was simply because there was such a bad example standing right here. I looked at the lecturer and thought, oh, you are killing it, man. You're meant to be explaining beautiful ideas to us and no one's listening to you, and you're killing it. I don't mean killing it in a good way. I mean, you're killing everyone's passion in the room. So I decided that I wanted his job on my very first day at university, and I needed a PhD to become a lecturer, so that became my next goal, that I will get a PhD in mathematics. And so I transferred to Bachelor of Science, and that was my path. And it wasn't until I got to third year that I had a moment where I could see where all this was going. And I had a third year lecturer who, as a throwaway line in some partial differential equation stuff he was showing us, said, oh, by the way, that equation can be used for modelling traffic flow. He moved on to something else less interesting. It's like, whoa, hang on, what did he just say? That can be used for modelling traffic flow. And I suddenly realised that the stuff we were learning could actually have impact in the world, and I wanted to learn more about that. He didn't teach me more about that, but that's fine. I knew that I was drawn to these practical applications. I studied some operations research and mathematical modelling. And I was more interested in trying to use mathematics to improve the world instead of the more abstract, pure stuff, and I still am. I did summer vacation work at CSIRO, where there are a lot of industry partners, and I got exposed to many different practical applications of mathematics, and then I did my PhD with them as well in the Maths and Stats division, and got a lot of exposure to industry work. But I still decided that I wanted to be a lecturer at the end of it, and didn't want to work for industry. So finally, the job that I wanted, well, I had to transition through working in IT, teaching computer programming and artificial intelligence and all these other things. And I eventually landed back in the mathematics area when I was a professor of mathematics and head of the School of Maths at Monash, etc., where I was finally able to teach mathematics to engineering students, but also mathematics students, and I was doing some research in mathematical modelling and optimisation. So it's been my journey to realise my dream of becoming a mathematician. So, what's Kate's theorem, I hear you ask? You all want to know what Kate's theorem is, right? It doesn't exist, sorry. There's no Kate's theorem per se, but of course I do have a lot of...
and take the pathway no matter whether it takes a longer way.
That's a theorem that needs no proof. Yes. So, but I do have a lot of research that I've done. You know, I've got about 10,000 citations to my work, and so, you know, there's no one theorem, but there's impact. I feel like I'm having impact with the work that I've done. I'm not so bold as to call something Kate's theorem. And so now I'm a professor of applied mathematics at University of Melbourne. What does that mean? So I share with you so you can give your students an idea of what it means to be an academic mathematician. I love my job because I have so much intellectual freedom just to do things that I find interesting. If I worked for a bank, I'd be helping them make money, and that's fine. I do some work with banks, but I love the freedom that I have, that I am free to choose which problems I find interesting, and that variety gets me out of bed every morning. I teach, I do research, I collaborate very widely with people in all sorts of industry and within the university context, biologists and all sorts of people. So I like to focus on having an impact in society with my mathematics through those collaborations, industry work, outreach to students, young people, and mentoring as well. And so, you know, this is a government publication just sort of talking about the importance of mentoring the next generation of mathematicians as well. So, as I said, all those problems I mentioned before, I've personally worked on those. So it's been a wonderful, varied career of feeling that the mathematics that I love makes a difference. So, what I wish my maths teachers had told me, because I had that one inspiring one in Year 12, but I've got to say I had my fair share of others that were memorable for other reasons, like telling me that girls couldn't do maths because we can't visualise in 3D, all that stuff. Anyway, let's not go there with some of the less inspiring ones. But what I wish my maths teachers had told me was that there's a growing skills shortage of mathematically qualified people. The world needs you to do mathematics. We need mathematical scientists to help us understand our world, to model it and improve it, and just to fill the world with logical, rational thinking people. I think the world would be so much better if everyone was just a little bit more logical and analytical in the way they think and, seek evidence for things. So, Sir Gus has it right when he says do as much mathematics and statistics as you can in your degrees. You don't have to do a maths degree. Whatever degree you do, fill your electives with mathematics and statistics. These skills will empower your professional life. Other things that I wish that I knew when I was 17, other maths-related things, I won't share with you all the other lessons I've learned in my life, but I wish that I knew that maths is a language. It's the language of logic and truth, and we use it to describe and improve the world. That maths holds the key to tackling so many challenges that we face in society, that it's creative, elegant, beautiful, and satisfying. It's not the procedural stuff. There's an elegance and beauty there that, as a musician myself, I'm obviously attracted to aesthetic things as well. I see that in maths as well. There are many ways to be good at mathematics. It's not just about whether you got a high distinction in the Westpac maths competition or something. Yeah, that doesn't define you as a mathematician, whether you do well in competitions. There's many ways to be good, and actually having really good people skills and being able to collaborate and problem solve is really important for many types of mathematics. There are many ways to have an impact in society through maths. I just really feel that students don't get this, they don't see it. The maths you see at school is foundational and preparation for the good stuff to come. So hang in there. And just as it always has been and always will be, maths is the foundation for so many careers. Maths is dynamic and responsive to society. And finally, I wish I knew when I was 17 that an inspiring maths teacher can really change your life. I wish I'd known then that maths teacher was having such a profound influence on me. I know she felt my gratitude because I dedicated my PhD thesis to her, and I used to visit her every year on her birthday for many, many years afterwards. But unfortunately, she passed away, and so I'd like to finish by dedicating this talk to the inspiration of Elizabeth Kerr there. And she was a wonderful teacher. And I might have a prize for anyone who knows who this person is. Some of you may recognise that person from a long time ago, but I won't give it away. Thank you. Wishing you all a wonderful conference.